Welcome back. In this video, I'm going to pick up kind of where I left off in the finding critical points video and use the critical points that we found in that video and just kind of finish up that process of figuring out local minima and local maxima using the second derivative test. So just to kind of remember what we're working with here, the second derivative test says that if the second derivatives of f of xy are continuous on a disk around the point AB, where AB is such that it makes the gradient of f equal to 0, then if we take this function dxy, which is kind of defined to be a combination of the second derivatives of f, specifically fxx at xy, partial derivative with respect to y at xy, and then minus the mixed partial derivative at xy squared, then we wind up with three possible cases for being able to sort this critical point here. So our first case is that when we take this whole thing here and evaluate it at our critical point, that this is greater than 0. And if this winds up being the case, then we have something further that we have to test. We need to check our partial derivative with respect to x, or our second partial derivative with respect to x at that point AB. And if this is greater than 0 as well, we have a local minimum. And if it is less than 0, we have a local maximum. This part right here is pretty much entirely the same as what you learned in Calc 1, like I said in the other video talking about the second derivative test. But we can only pass into this kind of test here if we check this guy first and it's greater than 0. Okay, so it could also be less than 0, this value d of xy, or d at AB more specifically. If it's less than 0, then we encounter something that you probably did not learn about in Calc 1, which is called a saddle point. And remember, this is when it's doing kind of different things in the x and the y direction. So maybe you have, say, a minimum in the y direction, but then it looks more like a maximum when you're looking in the x direction. Something kind of like that. And then our third possible case is when it's equal to 0. And this just simply means that it's inconclusive and there really isn't a whole lot else we can do with it. Oh, that is not how you spell that. Inconclusive. There we go. Okay, so let's just go ahead and get started with classifying critical points for functions that we worked with in a previous video. So our first example was f of xy is equal to x squared minus 6xy plus 2y cubed. Now, in our video, finding critical points, we found that this had critical points 0, 0, and 9, 3. So all we have to do is use the second derivative test to classify them. So that means that we have to compute, or at least first get this expression, d at xy is equal to fxx at xy, fyy at xy, and then minus that mixed partial derivative at xy, and then all of that is squared. Okay, so, well, we got to compute first partial derivatives, which pretty straightforward. It's 2x minus 6y, and the first partial with respect to y is equal to negative 6x plus 6y squared. Okay. So partial, or second partial with respect to x, that's just equal to 2. Second partial with respect to y, That's just equal to 12y. And then our mixed partial derivative is, I guess we'll just use this one right here. Take the derivative with respect to y. I'm going to get -6. Okay. So now this kind of gets me to a point where there's a couple of different approaches that we can take. We can either go ahead and take our critical points, plug them into this, and then use that to kind of compute D from there. My personal preference, especially when I have more than one critical point that I'm working with, is to compute the general form of this using these formulas here and then start plugging points in. So again, you can do it either way. You can plug points in and then evaluate this, or you can figure this out and then plug points in. But what this means, if I put all the pieces together, the general form dxy is going to look like 2 is going to go in for that partial derivative with respect to x, or the second partial, and then times 12y for my second partial with respect to y, and then minus the -6 squared. So this is just equal to 24y plus, minus 36. All right, so now all I got to do is plug my 2 critical points into this guy right here. So d at 0, 0 is going to be equal to 0 minus 36. Okay, so now at this point, that's just equal to -36. So I can come back here, look at my second derivative test here. We have the case that d was less than 0, which means that we have a saddle point. This was a saddle point at 0, 0. Okay, now we just have to test the other one, d at 9, 3. I'm going to get 24 times, times 3 minus 36. That is, I guess, 72 minus 36. I think that's just 36. Whatever it is, it winds up being greater than 0. So looking at my second derivative test here, greater than 0 means that I have to check my partial derivative or my second partial derivative with respect to x. Okay, so let's go back over here. My second partial derivative with respect to x, that's always equal to 2, including at the point 9, 3. Well, that's greater than 0. Means we have a local minimum. That's pretty much all there is to that process. The biggest part is really just going through finding your critical points, computing this d of xy thing, and then after that, it's really just kind of running through that second derivative test and floating through that chart, or however you've written up your little instructions there on how to mix and match greater than 0, less than 0, so on and so forth. Okay. Let's do another example. So this one was f of xy equal to y squared x minus 2x cubed minus y squared. We said earlier in our other video that the critical points were 0, 0, and 1 plus or minus root 6. Okay, so I guess we got 3 critical points there that we're looking at. Our second derivative test says that we have to start by computing this value, or this function dxy is equal to second partial with respect to x times second partial with respect to y minus mixed partial at xy squared. Okay, so partial with respect to x is y squared minus 6x squared. Partial with respect to y is equal to 2yx minus 2y. So now I'm going to get my second partial derivatives, and I'm going to get fxxxy is equal to negative 12x. Second partial with respect to y is going to be equal to 2x minus 2, and then my mixed partial is equal to 2y, like so. Okay, so now I can put these three pieces together into this right here to get my general expression for d at xy. And that's going to be negative 12x times 2x minus 2, and then minus 2y squared. I guess if you want, you could kind of distribute that through. I don't really see any point in that, but I am going to go ahead and square that right there. Minus 4y squared. Okay, great. Okay, so now we're going to go ahead and start plugging in our critical points into this guy right here. So d at 0, 0, that's going to be negative 12 times 0. Well, I guess that's 2 times 0 minus 2, and then minus 0. Well, that whole thing is just equal to 0, so the second derivative test is going to be inconclusive there. So we'll just kind of leave that alone for now. Test the other two. 1 root 6. I'm going to get negative 12 times 1, and then 2 times 1 minus 2. Well, this is just going to be 0. And so as soon as this is 0 and this term isn't 0, you know immediately that it's going to wind up having to be negative. In particular, this is 4 times root 6 squared. I really don't care what that comes out to be. I mean, it's simple enough to compute, but the big point there is that it is less than 0. Okay, because this guy is 0 and that's negative. So if it's less than 0, we can go back in and check. Greater than 0, we have to do the cases thing. If it's less than 0, we know immediately that it is a saddle point. So this is a saddle point at 1 root 6. Cool. One more left to check. D at 1 negative root 6 is equal to, well, this whole thing is going to be 0 once again because we're still just plugging in 1. And then we have minus 4 times negative root 6 squared. That's still less than 0. Well, same as before. That gives us a saddle point. All right. That wasn't too bad. Okay, we've got one more here. So our next example is going to be f of xy equals e to the y squared over 2 minus y minus x squared. Okay, we said earlier that it only had one critical point, and this was the point 0, 1. So applying our second derivative test, we have to compute dxy, which is equal to second partial with respect to x times second partial with respect to y minus the mixed partial at xy squared. Okay. So in order to fill this out, we have to compute all our partial derivatives. First partial with respect to x is just equal to negative 2x e to the y squared over 2 minus y minus x squared. I'm going to go ahead and compute my second partial with respect to x. So this time I've got 2x, which is a function of x, and e to the blah, which is also a function of x. So I'm going to have to use my product rule, and applying the product rule, we're going to get 4x squared e to the y squared over 2 minus y minus x squared, and then plus, let's see here, it's going to be negative 2 e to the y squared over 2 minus y minus x squared, just like so. Okay. And then I'm going to go ahead and compute the mixed partial as well. This one's a lot easier because we just need to take the derivative of this guy here with respect to y. No product rule needed. we're going to get negative 2x y minus 1 e to the y squared over 2 minus y minus x squared. Okay. And then, so first partial with respect to y was y minus 1 e to the y squared over 2 minus y minus x squared. And then second partial with respect to y is equal to y minus 1 squared e to the y squared over 2 minus y minus x squared. And then this is plus, got to take the derivative of this guy here. You get e to the y squared over 2 minus y minus x squared. Okay. Cool. All right, so we've computed all of our second partial derivatives and stuff like that. We're ready to start looking at this guy here. Although I'll be honest, with the big kind of mess that these derivatives are, this might be a case in which it is far easier to plug in the critical points first and then put all the pieces together here. So I'm going to go ahead and do that. So fxx at 0, 1. Well, I plug in 0 here. And that is just going to, oops, nope, we're looking here. This is just going to give me 0 minus, looks like 2 to the e raised to the negative 1/2, I think is what we're going to get out of that. So the big thing here is that this is a negative number. And then looking at fyy, at 0, 1, we're going to get something really similar. This guy right here is just going to be 0, but then we still have to deal with this piece here. That's going to be e to the negative 1/2 as well. All right, and then the mixed partial is super easy. This one's just 0. Okay, so one thing that's kind of nice about this, we're going to put all this together. So d at 0, 1. This guy right here is going to go in for this piece here. So I'm going to have negative 2 e to the negative 1/2 times e to the negative 1/2. That goes in for this here. And then minus 0 squared. Well, this is negative 2 times e to the negative first power. Doesn't really matter what the actual value of that is. That is definitely less than 0, which means that we have a saddle point. And that's pretty much all there is to that. Again, I just kind of want to emphasize that you can, I mean, like I showed here, you can either plug in your point first and then put all your pieces together, or you can put all the pieces together and then plug in the point. It doesn't really matter which way you go. The big idea here is that you first have to go through and find your critical points, like we did in the previous video, and then you just apply the second derivative test using this big thing right here, computing all of your different second derivatives. So, but then after that, it's all just plug and chug. So it's really not too terrible at all, but it can be kind of easy to get lost in the details of it. But hopefully this was helpful, and I'll see you next time.